Hello. In this video, we're going to look at higher order derivatives, which is section 3.2 in your textbook. Now, the motivation for this section is the question, what is the derivative of, let's say, x cubed? Well, we would do our rule for the power rule, and we get that y prime is equal to 3x squared. But then, what is the derivative of 3x squared? Well, you could do the derivative again and you get 6x. What's the derivative of 6x? Well, that'll be 6. Do the derivative of 6, that'll be 0. And so you get this idea that you could do the derivative and then another derivative and then another derivative. You could even call it maybe like a double derivative or a second derivative or a third or a fourth or a fifth. And you could just keep doing derivatives. So they're called higher order derivatives. And the definition is pretty straightforward. If fx is a differentiable function, then its derivative, dy dx, or f prime, or ddx, or df of x, right? These are all different ways of writing the derivative, so you might have seen this one and this one. Hopefully you've seen this one as well, and this one here is just another way of writing derivative. It's with a capital dx, it's so you can just get the whole derivative on one line, so you don't have to have that fraction. So the derivative is itself a function, which may or may not be differentiable. If f prime is a differentiable function, then its derivative is called the second derivative of f, denoted by either f double prime, or you could write y double prime. Sometimes people will write d squared y over dx squared. So the 2 here represents not like a power, but it represents like a second derivative. Or sometimes you can just straight define it as the derivative, ddx, of f prime x. So it's the next derivative, the second derivative. And in general, you could find the kth derivative. We usually write little brackets around the power, so we put f and then bracket k, or we'll write it as dk and then dx to the k, and it's defined as the derivative of the k minus 1th derivative. So the way you do the kth derivative is you just do the next derivative on and on. So let's look at an example here. We have a function. Fx is 2x to the 4 minus 5x cubed plus 2x squared plus 3x plus 7. Let's find the first 6 derivatives. So we'll find f prime x, which would be 8x cubed minus 15x squared plus 4x plus 3. We'll find f double prime, which is 24x squared minus 30x plus 4. We could find f triple prime, which would be 48x minus 30. We could find, well, really, I mean, you could find f to the 4, like the 4th derivative, but it starts to look a little silly with the tally marks. We usually will now put the 4 in little brackets for the 4th derivative, which would be 48. Because if you think about it, if you're going to write like f prime, 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 it just starts to look silly. And then it's almost like tally marks. Like, what are you going to do for the 5th derivative? Put like a tally mark? That's just a little bit silly. So we usually, after the 3rd derivative, just start writing the number up in brackets. So the 5th derivative would be 0, and of course, that'll make the 6th derivative also equal to 0. So there you go. We've got all 6 derivatives. Now, in general, if fx is a polynomial of degree n, then the n plus 1th derivative is going to be 0. Now, you might have noticed this as we were doing it. This was degree 4. So notice how different parts of the polynomial, they disappeared, or you can think of after each derivative, the polynomial decreased in order. It was degree 4, then it was degree 3, then degree 2, then degree 1, then degree 0, and then it was gone. It was just equals to 0. So after 5 derivatives, the degree 4 polynomial had disappeared. So what if someone gave you fx equals 10x to the 8 plus 4x to the 3 plus 11? If you had to find the 9th derivative, I mean, you could just do the derivative 9 times, but using this little remark, we know that it's just going to disappear. And so the 9th derivative is going to be equal to just 0. It doesn't work for other functions, but for polynomials, sometimes they disappear, which is kind of neat. Now let's also find a general formula. So if we had fx as 1 over x, let's see if we can find the nth derivative. Now to do this, of course we want to write this as x to the minus 1. And we want to start doing derivatives and see if we notice a pattern. So the first derivative is going to be equal to negative 1 x to the negative 2. The second derivative is going to be negative 1 times negative 2, x to the negative 3. The next one is going to be, well, negative 1 times negative 2 times negative 3, x to the negative 4. So hopefully we can see a bit of a pattern here. If we were just to write it out, the nth derivative would be, well, negative 1, negative 2, negative 3, because we notice for the third derivative we have negative 1, negative 2, negative 3. So for the nth derivative, we'd have all the way up, dot, 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 to negative n. Now the power on the x is a little more complicated. The third derivative had negative 4 on the power of x. So the nth derivative would have negative, well, not negative n, because if this was 3, then this would be negative 3. So if this is n, it's going to be negative n, and then subtract one more. It's going to be one more negative. Again, just to check that if it works here, this is 3. So negative 3 subtract 1 is indeed negative 4. Now this formula is good. It's definitely the valid answer, but we could simplify it a little bit. If we notice there's going to be, well, a negative sign here, a negative sign here, a negative sign here, there's going to be n negative signs. And then if we factor out those negative signs, we just have 1, 2, 3, all the way to n, which you might remember from pre-cal as n factorial. So we could rewrite this as negative 1, so we'll write f and the nth derivative is negative 1 to the n factorial, x to the negative n subtract 1. And that's a very nice closed formula. We don't have the dot, dot, dot in it anymore. This is a very nice and useful formula for the nth derivative of 1 over x. Let's go ahead and do another example. F of x is g of x over x, where g of x is a twice differentiable function. It means we can do the derivative twice. Let's find f double prime. So we'll start it off by finding f prime, which means we got to use the quotient rule. So low d high, derivative of that is just going to be g prime, less high, d low, derivative of x is 1 over x squared. We could simplify that a little bit. We'd get x g prime x minus just g of x over x squared. Now let's go ahead and do the second derivative. Well, we do low d high. Well, that means we have to do the derivative of this whole high thing. Let's do that on the side over here. D high. Well, the derivative of this portion is going to need a product rule. So derivative of the first is going to be 1, leave the second alone, g prime, plus leave the first alone, derivative of the second, g double prime. And then derivative of a difference is the difference of the derivative, so we subtract the derivative of g, which is subtract g prime. Now notice we've got a bit of a coincidence here. There's a g prime and a g prime. Those are going to cancel out nicely. So we just get x, g double prime x. So that's our d high. So low d high, x, g double prime x, less high d low, so 2x, over the denominator squared we go. And if you wanted, you could always expand it and simplify, but we can go ahead and leave it like this. This is a good final answer. Let's go ahead and try another one. F of x is x squared over 1 plus x. Let's find f double prime evaluated at 1. So that means we need to find f double prime, and then we're going to plug in the number 1. Again, to find the second derivative, we have to start with the first. So low d high, less high d low, over the denominator squared we go. Now it's nice to clean this up before we do the second derivative because, well, we're going to have to do another derivative. So we want to try to clean this up if possible, simplify the algebra. So we've got 2x plus 2x squared when we expand that first one, minus x squared. And the bottom we can FOIL out as 1 plus 2x plus x squared. That'll be equal to, well, we'll get just an x squared minus 2 plus 2x over x squared plus 2x plus 1. All right, let's go ahead and do the second derivative. So we get low x squared plus 2x plus 1. D high, that's going to give us 2x plus 2 less high x squared plus 2x. D low, 2x plus 2 over x squared plus 2x plus 1 squared. All right, so now we can plug in the number 1. So everywhere you see x, just replace it with 1. So you get 1 squared, which is 1, plus 2 plus 1. 2 plus 2 minus 1 plus 2. 2 plus 2 over 1 plus 2 plus 1 squared. So that'll be 4 times 4 minus 3 times 4 over 4 squared. So we're getting there. This is going to be 16 minus 12 over 16. So 4 over 16, which is 1 over 4. Let's try a multiple choice question. We're going to go ahead and calculate y double prime given y equal 3x to the 4 plus x to the negative 2. So go ahead and pause the video and give it a try. So assuming you gave it a try, we do the first derivative, which is 12x to the 3 minus 2x to the negative 3. And then you just do the derivative again. So 3 times 12 is going to be 36. Negative 3 times negative 2 will be positive 6. X to the negative 4. And, well, you could convert this here to 6 over x to the positive 4 if you wanted to make the exponent positive, which makes the correct answer C. Now, as a problem I want you to think about for the next video, what is the derivative of sine x? What's the derivative of sine x? Now, you might have seen videos and you might have an idea. Maybe you think the derivative is cos x. And that's certainly reasonable. Maybe sine and cos, they're both trig functions. Maybe they go together. Maybe that is true, but how could you prove it? In particular, you're going to want to do the definition of the derivative, right? With sine of x plus h minus sine of x over h. But, and this is very crucial, you can't expand this sine of x plus h with algebra. To expand this, you actually need a trig identity. So look at your trig identities and see if any of them apply here. See if you can expand this and work on it and simplify and maybe get an answer. We will look at this in more detail in the next video, but I want you to try the problem ahead of time. See if you can come up with the derivative of sine x. Again, it's more fun, more enjoyable, and really more rewarding when you try these problems yourself and you get a feel for the discovery of a derivative. So for homework, you can look at page 188, 27 to 30, and you can also look at the higher order derivative worksheet, which has some excellent examples. Hopefully you enjoyed this video, and as always, thanks for watching.